Aloha everyone! Today we're going to talk about maximum and minimum, and we're going to use the closed interval method to find the maximum and minimum of a continuous function on a closed interval. Some of the most important application of calculus is the optimization problems. Those problems can be reduced to finding the maximum or minimum value of a function. Today, let's see exactly what we mean by maximum and minimum values. So first we see that looking at this graph over here, in this graph over here, this point over here is the highest point, okay? So the y value of this point over here is the maximum of this function on this interval from here to here. And this point here is the lowest point. The y coordinate at this point is the minimum of the function on this interval. And that's called the absolute minimum. Okay, so 2 over here is the absolute minimum, and 5 over here is the absolute maximum. Absolute maximum, absolute minimum, they are the function value, the y value. The formal definition for absolute maximum or absolute minimum are stated here. Let C be a number in the domain of a function. Then f of c is the absolute maximum. Notice that that's the function value, okay? If f of c is greater than or equal to f of x for all x in the domain. So this function value, if it's above or equal to other function value in the domain, then that is the absolute maximum. Similarly, we define the absolute minimum. Absolute maximum or minimum sometimes is called a global maximum or global minimum. Okay, globally. Okay, so absolute maximum, absolute minimum is also called global maximum or global minimum. And they are called extreme values of the function because this is the maximum is on this extreme and then the minimum is on the other extreme. So those are called extreme values of the function. So when they ask you to find the extreme values of the functions, then that means they want you to find the maximum and also minimum values of the function. I have a graph over here. Notice that right now we consider the function on this interval from a and let's say to s over here. Now the graph look like this. Now looking at this graph, what is the absolute minimum? What's the absolute minimum here? Anyone?
The f of a?
Yes, f of a is the absolute minimum. Looks like the function value is the smallest on this interval from a to s, right? Yes. So absolute minimum is f of a. That's the function value. Okay, right. Absolute maximum here is f of d, this function value over here at this point. That is the largest function value on this domain from a to s. Now, some of you will say that, what about this one, this one, this one, this one? Now, when you're looking at this point over here, when x equal to b, on the left side and the right side here, okay, looking at this open neighborhood, so neighborhood, it has the left and the right, and looks like this point here is the highest point in this neighborhood, right? The function value over here at this point is called the local maximum, okay? So locally, this is the highest point. So FB over here, the y coordinate at this point is the local maximum. It's the local maximum of this function. Similarly, FD over here is also a local maximum. Now this one over here, FC here, is a local minimum because locally this is the lowest point. And also this one, locally this is the lowest point. Now, as you can see here, FD is the absolute maximum, also is a local maximum. Okay, so in this neighborhood, that's the highest point, but in the whole domain from A to S, that's also the highest point. So FD here is local and also global maximum. Okay. Now, what about this one here? This one here is not, FA here is not a local minimum because it doesn't have this left neighborhood. So only have the right neighborhood right here. So on the left side, it's not in the domain, okay? And only have the right neighborhood. So this one here is not local. Similarly, this M over here is not local. This one here has no right neighborhood. To consider to be local, it has to have the left and the right neighborhood. Okay? You guys got it? Understand?
Understand.
Okay, that's great. So over here, FA is the absolute mean. This is the local max. This is the local mean. FC is local mean. FD is absolute and local max. This is a local mean. And that is, well, over here is neither. It's not local and it's not absolute either. Okay. Okay. So the definition for a local max and local mean is stay over here. So if the function value fc is greater than or equal to f of x, when x is near c, so consider this neighborhood over here. When x is near this b over here, then the function value is bigger than or equal to the function value at this neighborhood. Okay, then the function value at this point is going to be a local max over here. Okay, when they say near that point, that means you need to have some open interval containing that C over here. So that you need to have a left and right neighborhood, okay, open interval. Okay, now let's take a look at this function. Can you tell me, oh, well, it's already stay over here, okay. So you see that the local and absolute maximum is equal to what? What is it equal to? What's the local and absolute maximum?
Is it f of 2 pi or?
F of 2 pi and f of 0. And what does it equal to?
Is that 1?
This is the function cosine x, right? Cosine of 2 pi is equal to 1. Okay. And cosine of 0 is equal to 1. So the absolute max over here is 1. And also it is a local max because you can have a neighborhood, small neighborhood here. That's the highest point. What's the absolute mean?
Negative 1.
You got it. So it's negative 1. Okay. Next one. This function, x squared. What's the absolute mean?
0.
You got it. Is it also a local mean?
Yes. Yeah.
You got it. Okay, what about absolute maximum?
There's none.
Yeah, there's none.
We can say infinity.
Infinity is not a real number. To be a maximum minimum has to be a real number. Okay, yeah. So there's no absolute maximum over here. Okay, and keep on going without boundary. Okay. Okay, now x cubed. What's the absolute maximum?
There's none.
None. Absolute minimum?
There's also none.
None. You got it. Good job. Okay, now this one over here. What's the absolute maximum? Looking at the graph.
Is it 37?
37. You got it. This point here is the highest point on this domain from negative 1 to 4. So 37 is highest function value on this domain from negative 1 to 4. Yes, you got it. Okay. What's the absolute mean?
Negative 27.
Negative 27. You got it. What's the local max? Local max?
5.
5? Yes, 5 over here. So you see that over here you can have, at this point you can have an open neighborhood around it, okay? And this one is the highest point in this open neighborhood. So the y value here is the local max. This one here is not local, okay? This one doesn't have an open neighborhood, and this one doesn't have an open neighborhood either. Okay, what about local mean?
Negative 27.
Negative 27, yeah. In this neighborhood, this function value is the lowest. So negative 27. Okay, good job. Okay, now consider a continuous function on a closed interval. Now I have 3 cases over here as stated. Okay, so I have continuous function. What does it mean continuous? That means it has no break. So if you're looking at the graph right here, you see there's no break. Okay, so a continuous curve, there's no break. On this closed interval a to b over here, okay, so it could be like this, this, and this. What do we observe? If the function is continuous on this closed interval, then the function must attain an absolute maximum and absolute minimum somewhere inside this closed interval. You see over here, this is the highest and this is the lowest. Absolute max, absolute mean here. And then absolute max over here, absolute mean over here, absolute max here. These two actually could be equal. So you can have absolute maximum at two different x inside the domain, okay, like this too. And then absolute mean over here. Now this one over here, the function here is a constant function. So absolute max is 1. Absolute mean here is also 1. So you could have the absolute max and absolute mean to be the same function value if it's a constant function. Looking at this, so you think about, you had come up with this idea, right? So if it's a continuous function on a closed interval, then guarantee that you will obtain an absolute maximum and an absolute minimum somewhere on this closed interval. And that is a theme. Okay, it's called the extreme value theme. So what does it say? So if the function is continuous on a closed interval, then the function attains an absolute max and an absolute mean somewhere inside that closed interval. As you can see from this picture over here, you can try to picture them. So somewhere, guarantee that it's going to attain the absolute max and absolute mean. So it's kind of like the Easter egg hunt. I say, I'm going to hide the egg somewhere inside the room. I said, guarantee that you're going to find that somewhere. You just need to find the location. But it's guaranteed they're going to be there. Okay? Okay. There are two hypotheses for this. There are two conditions for when you apply this thing. Okay? Number one, the function has to be continuous. Number two, it has to be a closed interval, a to b. Now, if you take away one of them, then this conclusion is not guaranteed. Say we take away the first condition. If the function is not continuous, we can have this function like this. It's not continuous at 1, but then on this closed interval from 0 to 2. Does it attain absolute maximum? Well, notice that, okay, so you can see that over here is an open gap over here. See, this is an open circle over here. So the function is discontinuous at 1. This function here has no absolute maximum. It can get really, really close to, the function value can get really, really close to 3, but never attain 3, never reach 3. So this function here has no absolute maximum on this domain from 0 to 2. So if I take away the function to be continuous, then there's no guarantee that the function attains absolute maximum. Okay, so this condition is necessary for that to have this conclusion. Now let's take away the second hypothesis, the closed interval. Okay, so the function is continuous, however, it's not on a closed interval. Then it's a guarantee that the function attain a maximum and minimum on that interval. Well, let's see over here. This function is continuous on this open interval. So instead of closed interval, we have an open interval 0 to 2, like this. And this one here is an open gap. You see, it's an open gap. Now, this function here has no absolute minimum. The function value can get really, really close to 1, but never reach 1 over here. So this one here has no absolute minimum. Does it have an absolute maximum? Does it have the absolute maximum?
No.
No, neither. This one keep on going up and going up without boundary, right? So no absolute minimum, no absolute maximum. This one here, no absolute maximum. Okay. So the two hypotheses are necessary in order to have that conclusion. Number one, function has to be continuous. And number two, it has to be on a closed interval in order to guarantee that the function attain absolute maximum and absolute minimum on that closed interval. Now, so we know that it's guaranteed that if a function is continuous on a closed interval, and it will have absolute maximum and absolute minimum. So somewhere on that closed interval, you get the absolute maximum, absolute minimum. Okay. So, but where do you find them? Okay. Where to find them? So it's like the Easter egg hunt. So it's like, okay, somewhere in the room. Okay. But where do you find them? Okay. So the location for those absolute maximum and absolute minimum, we're going to talk about where to find them. So let's first think about this case and this case. This is a continuous function on this closed interval a to b. Looks like I have a maximum here and minimum here, right? What's so special about this point and this point? What do you observe about the tangent line? What kind of tangent line at these 2 points?
They're both 0.
The slope equal to 0, right? Yes. So if I draw a tangent line, then it's going to be horizontal. So which means the slope will be equal to 0. So f prime of c will be equal to 0 when c here is the c1 or c2 over here. We see that absolute max and absolute mean, and at this 2 point, the duality at this c1 and c2 will be equal to 0. The slope of the tangent line equal to 0. Okay, so that gives us a hint that we might look at absolute max and absolute mean at the place that the duality equal to 0. Now, looking at this one over here, this function is continuous on this closed interval a to b, and you see the maximum over here and the absolute minimum over here. What's so special about this at this point? Now, this one over here is a corner.
Does that mean that it does not have a slope?
Yes, you got it. Now, as you recall from the early in the semester, we talk about when you have a corner, then it is too sharp to have a tangent, okay? And the duality will not exist at this point. So the left duality or the right duality, they don't agree, right? So the duality here does not exist at this point. You got it. So the duality does not exist over here. But the function value is the absolute minimum, okay? Now what about over here? This is the absolute maximum, but it is at the end point. Remember before we talked about when you have a corner or when you have a kink, then at the corner or at a kink, it will be too sharp to have a tangent. So the duality will not exist at this corner or this kink over here. Okay, so that will give us some idea. We can start looking for absolute maximum and absolute minimum at the place that the first duality equals 0 or the first duality does not exist, or at the end point. So you first look at the local maximum and local minimum first, and then later on compare them with the endpoint value, then you can find the absolute max and absolute min. So it's like a competition, right? So locally at your school, and later on you're going to compare that with everyone in the city, and then later on, then you get the winner in the whole city. Start looking for local max or min at those C where the first duality equals 0 or does not exist, and then later on compare the function value at C with the endpoint values. All right, so do you get the idea? So we first find potential local max and local min at these 2 places, and then later on we're going to compare those function value with the endpoint value to find the absolute max and absolute min. Okay, so this one here involves the Fermat theme. Okay, Fermat is famous for his last theme, but he has a lot of themes. So this is one of his themes. It says that if a function has a local max or local min at C, and if the duality at C exists, then the duality will be equal to 0. So if it's a local max and local min, that means either the duality will equal to 0 or the duality does not exist. So those are the possible places for local max and local min. But vice versa, if the duality equals 0, it's not necessary for the function value to be a local max and local min. So it goes this way. If it's a local max and local min, then the duality either equals 0 or does not exist. But if it goes the other way, it's not true. Okay. For example, over here, looking at this graph here, this function, when C equals 0, the duality is equal to 0. Okay. This is the XQ function. So y prime is 3x squared. At 0, when you substitute 0 into x, you get y prime equal to 0. So the duality will be equal to 0 at 0. However, f of 0 here, this function value is not a local max or local mean. So goes this way, but it doesn't go the other way. So the converse of this is not true. Okay, so only go this way. Any question? Okay, I will answer your question. Okay, so the question here is why f prime of 0 equals 0. Okay, so this function here is f of x equal to x cubed. That's the x cubed function right here. So differentiate that, we get 3x squared. Now you substitute 0 into x. So substitute 0 into x. So 3 times 0 squared, and what does it equal to? You get 0. Right, you get 0. So f prime of 0 is equal to 0. However, the function value here at 0, is it local max or local mean? It's not. So, but this function value f at 0 is not local max or local mean. Okay?
We have to calculate to get a 0, not by looking of a graph, right?
To get a 0? Yeah.
Because if
So looking at the graph, you can see that the tangent line is actually horizontal, right? Do you see it's horizontal tangent? Yeah. And then also you can check over here by substitute 0 into x, you get f prime of 0 equal to 0. Okay.
Thank you.
Okay. So Fermat theme that we just stay. So suggest that we should at least start looking for the extreme values and where the function has the duality equal to 0 or does not exist. So those numbers are given a special name. So those C over there. So what are those C? Those C in the domain where the duality equal to 0 or does not exist. Those C, we call that a critical number. See, critical numbers start with a C. So let's put a C there. Okay. So critical number. So to be a critical number of the function, then that number C have two conditions. Number one, it has to be in the domain. If it's outside the domain, it's not a critical number. Number two, the duality either equal to 0 or does not exist. Okay, let's use this example to illustrate this definition a little bit more. Okay, now let's find the critical number of this function. First, I want you to find the domain for this function. What's the domain for this function? Well, it looks like this one here, it doesn't involve even root, right? And it's not in the denominator. X is not in the denominator. So the domain for this is actually all real numbers. Or you can put down negative infinity to infinity. Now we're going to look for a critical number inside the domain. So first, we're going to differentiate that, and then we try to find out when the duality equals 0 or does not exist. So differentiate that, we use what kind of rule to differentiate? Well, this is a product. So we're going to differentiate, use a product rule. So use the product rule, differentiate this. Differentiate the first function, and what do you get? Use the power rule to differentiate this first function. So you bring down this exponent, 3 over 5, and then x to the what power. Exponent here decreased by 1, so that will be
negative 2 over 5.
Negative 2 over 5. Now times the second function. Now adding the first function times the duality of the second function. Now what's the duality of the second function?
Is it negative 1?
Negative 1. Okay. Now simplify this. We got this. How do you got this? Well, this one over here is this one over here. This one over here is this one over here. Okay. And now you combine them using the LCD, which is this. And then you have this. And do the algebra. Okay. You come up with this. Okay. Now, after you differentiate that, you're going to set this equal to 0. We're trying to find critical number, right? Now we're going to set the duality equal to 0 or find out when the duality does not exist to find critical number. So if I set this equal to 0, this equal to 0 only when the numerator equal to 0 and the denominator does not equal to 0. When will this numerator equal to 0? When x equal to, when will the numerator here equal to 0? When x equal to 1.5. Yes. Which is 3/2. Good. And when will this be undefined. This will be undefined when the denominator equals 0, right? When will this denominator equal 0?
When x is 0.
You got it. Now, since the domain is all real number, so these two numbers, they are in the domain, so they are the critical number. Got it? So you see how you find critical number? So the critical number is you first find the domain of the function, and then later on, you differentiate that. You set the derivative equal to 0 and find out when what x corresponds to that. And you also find out when the derivative will be undefined. And you find the corresponding x for that. And see if they're inside the domain. If they're inside the domain, then they are critical number. If it's outside the domain, then you can discard it. So for example, if this one is outside the domain, then you can discard that and you only have the other one. Okay, so that's how you find critical numbers. Okay, so in terms of critical number, Fermat theorem can be rephrased as follows. So if the function f has a local max and local mean at c, then c is the critical number of the function, which means that the derivative will be either equal to 0 or does not exist at c. Okay, now how do you find absolute max and absolute mean then? So to find absolute max and absolute minimum of a continuous function on a closed interval, then the way that you do it is you will try to find possible local max and local mean inside this closed interval. Okay. You look for potential local max or local mean. And then later on, you compare those function value with the endpoint function value. And then the highest one is the absolute max. And the lowest one is the absolute mean. Think about like having a competition, right? So locally at your school, you might be the number one, okay? And then later on, you go out to a bigger area, like the whole city, okay? And then you want to compare that with this two endpoint, okay? And then so whichever is the highest, then is the absolute max. Whichever is the lowest is the absolute mean, okay? So you find the potential local max and mean inside the interval, and then compare with the endpoint value to find absolute max, absolute mean. So we have this closed interval method. So when you have a continuous function on a closed interval, so what do? So now you will consider this closed interval as a domain, and then you will find the value of f at the critical number of this function inside the open interval a to b, and then you also find the endpoint value, and then you compare them. The largest one is the absolute max, and then the lowest one, the smallest one, is the absolute mean. Okay, let me give you this example over here. Let's do this together. Let me outline this step for you. So the first step here, you want to state the domain. So make it clear what's the domain. The domain over here is this closed interval. The second step here, you will differentiate the function to find critical numbers. So differentiate this. This is a polynomial. Differentiate this, what do you get? So you have 3x squared minus 6x, right? Now you're going to factor this because we try to find when will this equal 0. So you factor into this, and you try to find out when this derivative will be equal to 0, or when will this be undefined. When will this equal to 0?
When x equals 0 and when x equals 2.
Yes, when x equals 0 and also 2. When will this be undefined? Since this is a polynomial, it's never going to be undefined because domain for polynomial is all real numbers. So let it happen, okay? So the critical numbers of this function will be those numbers inside this domain. So let's see if they are inside the domain. Is 0 inside this domain?
Yes.
What about 2?
Yes.
Yes. So both of them are critical numbers. You found the critical numbers, and then step C is to draw a table. So this table will make it 2 rows. So the first row for x, second row for the function value f of x. The function here is, and then now you're going to put the 2 endpoint at the 2 end. So this end is negative 1/2, the other end is 4. Now, and then you put the critical numbers in it. You write down those x value, the endpoint at the two ends, and you put down the critical number inside here. And then now you find the corresponding function value. If I substitute the x to be those values, I will get substitute into x, and we find the function value. So trust me, those are the function value when you substitute those x in it. Okay. The function value at the critical numbers are potential local max or local mean. The function value at the two ends, and then those are the endpoint values. And then now you can just compare them. How do I get this one? The 1/8. I will just substitute negative 1/2 into this x, and then I calculate that, I'll get 1/8. Okay. Similarly, I got those function value by substituting x to be different number over here. Now you're going to compare this, the local max and local mean, with the endpoint value over here. Actually, I shouldn't say those are local max and local mean. Those are the possible local max and possible local mean. Okay, possible. Okay, and then we're going to compare the values of those values with the endpoint values. So what's the absolute max and what's the absolute mean of the function on the closed interval from negative 1/2 to 4?
The absolute max is 17.
You got it.
And the minimum would be negative 3.
You got it. So this is the absolute max and this is the absolute mean. This is the highest value over here. This is the lowest value of all of them. So absolute max here, absolute mean over here. So the 3 step here is what I do using the closed interval method. Okay, first I state the domain, that's closed interval. And then later on, I differentiate the function, find out when the derivative equals 0 or does not exist. Okay, and then you got those critical number inside the domain, and you put the two ends, you put the critical number inside, and then you compare the function value over here to get the absolute max and absolute mean. Okay, I'm going to write down the steps. Okay, one more time. Closed interval method, let's call that CIM. So first step, you write down the domain, which is a closed interval that is given. Second step is you take the first derivative. You find when the derivative equal to 0 or when the derivative is undefined. And then you're looking at those x value and see if they are inside the domain. This step over here is for you to find critical number. So you find critical number by differentiate that, and then also check this here, and then see if they are inside the domain. If it's inside the domain, they are critical numbers. And then the next step is to make a table, because instead of using paragraph, so a table is easy to see and you don't have to write paragraph after paragraph. For the table, you have this x for the first row, f of x for the second row, and you put down the endpoint here, and you put critical number in between. And then we're going to compare the function value that you got. Whichever that is the largest over here is going to be the absolute max. And the lowest one, the least one, is going to be the absolute mean. So that's called the closed interval method. So the book didn't make a table, but they use a paragraph. They say, oh, because this and this and this. But I think that a table is better than 1,000 words. So I just make a table this way. So that's just my way to do it. So that's called the closed interval method. It's for a continuous function on a closed interval. And those are the 3 steps for you to find absolute max and absolute mean.